In class, you'll recall that I pointed you towards two different tables that show up at the back of our textbook, but also that are in the notes here. So I have one of them shown here, and I've also separated them out from the PDF textbook and posted them as part of the first module on Canvas. And these tables give important properties of some of the common distributions that we'll work with, and so they'll be really important. It's a good idea to have them on hand. But I wanted to focus in on something that shows up in some of the PDFs listed on this table. So let's zero in for a minute on the exponential distribution, which hopefully you remember from your prereq course. But you may not have seen the PDF of the exponential written in quite this way. So typically we see the PDF as something like lambda e to the negative lambda x, and then we make some statement about where this definition holds, for what values of x. And it turns out, if you remember, for the exponential distribution, it's positive real numbers. So for negative real numbers, or 0, the PDF of the exponential is 0. And so it's always a little bit awkward to have to say that, or after the function write down the values of x, or define it as a piecewise function, which is maybe what you did in your prereq course. There's a more compact and more concise way to do that, and that's with indicator functions. So what I've highlighted here is an indicator function, and what it says is that the value of this indicator function will be 1 if x falls in the interval listed there. So that means if x is between 0 and infinity, so if it's a positive number, then that indicator will be 1, and that leaves us with the exponential PDF of lambda e to the negative lambda x. But if x falls outside of this interval, so namely if it's 0 or a negative real number, then the indicator function will be 0. And that means that this PDF will be 0, which is exactly what we want in the exponential case. We don't want any probability mass over over negative values. So indicator functions will be really useful to us. We'll use them in a lot of contexts when we write down PDFs, so that we always remember the support of the distribution, or we could also call it the domain of the PDF. So to be a little bit more general, we can define indicator functions in the following way. So we can let A be any set. So for the case of the exponential, A was the set from the interval from 0 out to infinity. So here we'll be a bit more general. A is just some set, and we'll say that the indicator function over A as a function of x will be 1 if x is in A, and 0 if x is not in A. So it's a simple idea, and it just makes the writing down of PDFs quite a bit easier. So we looked at an exponential example. Why don't we look just at another simple example, maybe the uniform distribution. So suppose we have our x coming from a uniform, we'll make it AB. So the PDF will be a function of x. It will have two parameters, a and b. And you may have written down the PDF in your prereq course as something like 1 over b minus a. But of course you have to specify the values for which x can take on where this is the case. So you could do that by maybe making this piecewise and say, well, that's only true for all x in the interval from a to b, and then it's 0 otherwise. But an alternative to that is to just write the indicator function. So multiply by the indicator function, where a is now the interval from little a to b, and it's a function of x. So this conveys the same information. It says, well, you've got the interval from A to B, and on that interval, the PDF should be 1 over B minus A, and everywhere else, it's 0. So again, this will be really helpful going forward, so I hope that you get a sense of how this works, and you get some practice using indicator functions on the homework.